to my GYPT presentation about the 16th experiment, which is called Saving Honey. At first, what is the experiment actually about? Well, given is a rod which at its top holds a viscose liquid, for example honey. Usually the liquid will run down because of gravity, as we all of course know. But if spun, the liquid will actually stop running down. How can this be explained? At first, I'm going to show you my experimental setup. There are two main components to the setup that I used. At first, the direct current motor, which can be seen in the left half of the picture. Then in the right half of the picture, there is our rate of revolution gauge, and also the two honeys that I used in order to test the effect. Here is the setup with the very viscose honey, and here the one with the less viscose honey. Now, there were some main questions I had to answer. First, which main characteristics of the liquid is responsible for preventing the honey from running down, but instead having it stay elevated? And how can the rod be spun with a constant velocity? How can the current amount of honey on the rod be measured? And does the effect work better with higher or lower velocities? And is there an optimum under certain circumstances? And also, which influence does the form of the cross-section have on the effect seen? Now, which main characteristics of the liquid is responsible for the effect being seen? It's of course the viscosity of the liquid that we use. And viscosity generally describes the state of a fluid of being thick, sticky, and semi-fluid in consistency due to its internal friction and cohetic forces. There are two main kinds of viscosity. At first, dynamic viscosity and kinematic viscosity. Dynamic viscosity is the one that is seen in effect here, and its unit is Pascal seconds. The forces can be calculated using a formula that you can see down here. Explain the honey staying up. We could, of course, calculate the velocity of the honey spilling down if we adjust the formula of the viscosity, but this would only work in a laminar stream, which we actually don't have here. And if we have had the velocity, we would also be able to calculate the distance traveled by the honey using the time for a rotation, knowing the angular velocity is 6 pi per second, and there is a certain downpull. Then we also know that the radial force is stronger by the factor of the radius, but I will come to that later. So how exactly does this work now? Well, there are several forces influencing the honey. At first, the centripetal force caused by the radial movement of the rod, which can be calculated using either this formula or the one that I'm going to show you on the next page. And there is also weight influencing the honey. So does the centripetal or radial force matter? In short, it doesn't, at least at first. Well, if we calculate the centripetal force for the start, we can see that it's not greater than 0.0003 newtons. And that isn't enough in order to explain how the honey stays elevated. And it's also directed outwards, so it would just at first squeeze it down and then pull outwards, so it wouldn't explain how it stays elevated. Now, how can the effect be explained if the radial force doesn't matter? There is no constant force which pulls the honey, but rather a changing one. The weight pulls the honey down to a certain degree and with certain forces. but the rod keeps on spinning and the honey is pulled out and also kind of wrapped around the rod because of its own inertia, thus explaining how the honey cell is elevated, which also can be seen in the little sketches now on the down right portion. How can the rod be spun with a constant velocity? Well, I used a direct current motor that was formerly used in a drill. I attached the rod in front of the motor, and after that I measured the angular velocity using the rate of revolution gauge that you could see in the first picture of my experimental setup. The maximum angular speed that I got was 6 pi per second at 12 volt. And how can the current amount of honey on the rod be measured? Well, we did this beforehand. We measured the mass of the honey using a scale, and then I calculated the volume using its density, where we would get the volume of about 7 milliliters. And at which velocities does the effect work best? Is there an optimum under any circumstances? Well, it does work better at lower velocities, because then the centripetal forces aren't strong enough to pull the honey out and overcome the cohetic forces between the honey molecules. Now, you may be confused because I said that the centripetal force would not matter. Well, in the effect that which I discussed here, it doesn't matter. It doesn't explain how the honey stays up. But it does explain how the special thing that I actually saw worked. So at very high velocities and with a very viscose honey, I could actually see the honey was pulled outwards too much in order for it to wrap around the rod, but instead it being dragged onto a point that the cohetic forces, which usually would hold the honey together, weren't strong enough to hold it together anymore, and the radial forces, which squeeze the honey outwards, are so great that they are able to overcome these cohetic forces and sending the honey flying into any direction, which can be seen now. Main question: which effect does the cross-section of the rod have? I think that with a parabolic shaped cross-sections, the velocities needed to keep the honey elevated would be much lower, as the forces influencing the honey would mainly press against the parabolic shaped cross-section, thus making the velocities needed for the honey to be dragged outwards much greater. But I did not do an experiment in order to determine this effect, because I wanted to eliminate all the irregularities that would come with a parabolic shaped cross-section, and I wanted to focus on the flat surface that we used for our rod. Now I thank you for your attention, and I hope you liked my experiment.